with where you started last week, because if I remember rightly, what I'd done was we'd done how to write the expression for the impedance, and then I was off the week after that, so we didn't get to do any calculation of the current. I didn't get to teach you that. All right, so let's find out what you know how to do without the solutions. So we've got a capacitor of 150 microfarads. Oh no, that's capacitor 220 microfarads. In series with 4 ohms. Connected to, or have a step input of 100 volts. Okay. Now, the exam question is possibly that's going to ask you to draw the circuit and label the components with their S-domain impedances. So, how do I do a capacitor C in the S-domain? Yeah, so that you would write that as 1 over 220 by 10 to the minus 6 S. Yep, if you've got to label it like that. And the resistance is just 4. Yeah, no units, no S, no nothing. So if you're asked to do that, that's what I was asking you to do. Write the components with their S-domain values on a diagram. Alright, and this is the correct symbol for a step input to up from 0 to 100 volts. Alright, so where do we start with solving that problem? Yeah, we write an expression for the impedance in the S domain, which is for the resistance plus in actual fact, I think in this instance that's probably less confusing and easier for the rest of the problem if you route that impedance as 0.3022 S. Alright? Sometimes it's just easier than using the times notation. Keeps things together. Alright? So we've got that. Now what do we do? Yeah. So we could say, well, first of all, I is V over Z. Yeah. In the time domain, isn't it? Yeah. And Vs is, how do we write from the Laplace transform table? How do we write step voltage? 100 over S. Yeah. So now we can write an expression for the current in the S domain, because it is V 100 over S all over the impedance, which is 4 plus 1 over incidentally, from your electrical knowledge, what shape of graph are you expecting here over time? you think it does that? Well, it starts at time is equal to 0. The current will be 0 is what you think, yeah? And then that's going to do an exponential rise to a limit. Right? We'll check that out when we get there. So when we get a current, we'll graph it when we get an expression for current and see what it looks like. Alright? So, what do we do with that? How do we divide a fraction by another fraction? Because technically we could look at this one as being over 1. Like a fraction divided by a fraction. How do we deal with that? Yeah, you turn the denominator fraction upside down and multiply it. Okay, so we rewrite that as 100 over s times 1 over 4 plus 1 over. I should have a 2, 2 there, shouldn't I? Yep. Alright. So when we get to that position, we got one fraction divided by another fraction. We turn the bottom one upside down and multiply. Okay. That can be multiplied out. So we can say IS is equal to 1 times 100. On the top line is 100. We've got 4s plus s over 0.3022s. What can I do to that? Yeah, these two s's will cancel out, so that cancels and becomes 1. Please don't make the mistake of dropping it completely. That cancels out. So that part there becomes 1 over 0.0022, which we can now turn into a number. So we get equals 100 over 4s plus, just check, make sure my calculations are right. I got 4545. Just check it, please. Jasmine, what do we do next? What we got? What's one we need to aim for here? We're aiming. Remember, we're aiming for it to look like one of the expressions in the Laplace transform table. Yeah, we need to get s on its own. So let's just make a note of that here. What do we do to get s on its own? We divide by 4. Yep. So we divide this by 4. The 4 in front of the s will disappear. So that leaves us with 100 over 4 is 25. We end up with s there plus 1136. All right. Everyone agree? my S look a little bit more like an S, I guess. All right? Now, that looks like I over S plus B in LT type. Yep. Two. So if we got I over S, a constant over S plus another constant, it transfers back to IT is equal to I B to the minus dt amperes. Yep. So that's looking at that table and transferring back. So all the time you're doing your manipulation in the S domain, you're trying to get your function to look like one of these functions in the right hand side of the table so that you've got the constants to transfer back to the time domain. Yeah. Therefore, IT, notice as a lowercase I because we're talking about an instantaneous current over time, is equal to I, which is 25, times E to the power of minus B 1136 T. Yep. That is the function for that circuit over time from a step input. So is the shape of our guessed graph correct, do you think? Don's guessed graph. Yeah. Quite a guess now. Do you want to carry on writing that down? So we graph that function. We start at time e is equal to 0, 25. Yeah. And we go down to almost 0. Yeah. Not really. All right. Just go back to here and look at the circuit. Can we explain that? Right. At time is equal to 0, what's the voltage across the capacitor? 0. Therefore, according to Kirchhoff's voltage law, what's the voltage across the resistor? No, these two have got to add up to 100, remember. So we got 100 there. Therefore, the current is, through that resistor, 100 volts over 4 ohms, 25 amps. Yeah, and then as the capacitor charges up, you get less voltage across the resistor, and therefore the current goes down. Remember that from science, time constant, and all that? Okay, so it never ever really reaches 0, but we assume it reaches 0 when the current's so small you could measure it. Remember doing that experiment, the experiments in science around this. So there's an exponential decay, and that is what we would expect for that circuit. All right? So that's wrong. We actually expect it's well, that's no problem with it being wrong. But it's useful to understand what you might expect to happen, and therefore you might be able to answer a question like that in the exam. Sketch the graph that you are expecting, or sketch a graph of the function you get in the end. All right. So if you can explain what you think about what you think might be going on to start with, then you know if you're in a more complex circuit, the part around capacitor charging is going to look like that. Okay. So I'm happy with that question. Yeah.